Boom, there it is. Heck yeah. Look at that, we're rolling. We are rolling, people. We're doing good. We're doing good. Alright, that is what I like to see. Whoops, actually, why did I just... Oh, that was correct. Man. Alright, so what did I want to do today? I very much wanted to look at some things. Oh, windows. I want this window, like, here. Ah, we gotta go with that. Alright, the AI assistant battle.
Hey, what's up, guys? MKBHD here. Okay, so we've already done Google Assistant versus Siri versus Alexa and Cortana and all of that. You can watch that video if you want to. But that very much feels like level 1, where this, as you'll see, very much levels up. Now, ChatGPT has been getting like a lot of the shine. Like, I've made a video about it. You've probably watched other videos about it. And once we saw it get built into Bing and kind of go crazy, that's when we knew Google's probably gonna have a response at some point. And now it kind of is out when we have Bard. Okay, quick interjection. I should have put this in the main video, but I didn't, but I'm gonna say it anyway, which is that these are also really quick moving tools. So Bard is gonna actually continue to improve. GPT is gonna continue to get better and more capable. The gap between them could shrink over time or it could increase. We don't really know, but this is just a snapshot in early April 2023 of how good these two are. Just figured I should mention that. Okay. And so I wanted to put them side by side and ask them the same questions and figure out which one is potentially more helpful right now, which one feels like it's more ahead. So first of all, I just want to highlight some visual differences between the UI of the two. So the new Bing with ChatGPT, it feels much more like a finished product, like something they want a lot of people to use. And then as you talk to it, you're limited to 20 queries in one conversation. And it also has this creative versus precise slider for conversation style. Then Google Bard looks like a Google product, I would say, pretty clean. Also, when you're typing to it, the question doesn't type out, but it just kind of pauses for a bit and then just slams you with the whole answer. But then when you do get an answer, it has a thumbs up, thumbs down, a new answer, and Google it. And it also has 3 drafts of every answer, so you can see what some of the worst drafts that didn't make it look like. I've also noticed generally Bing, when it brings things in from other websites, tends to cite its sources more often, and Bard will do that once in a while. Okay, so let's start with the first category, which is just simple questions. I want to ask you things here that I already know the answer to, so I can also do some fact checking, because a big part of these things is that sometimes it will lie to you if you don't know what you're talking about. So let's start with, what's the best camera in a smartphone? So Bard is saying the best camera in a smartphone is the one that takes the best pictures for you. Sure, I agree. It goes on to list S23 Ultra, iPhone 14 Pro Max, and Pixel 7 Pro. But ultimately, I think all of these things here are correct. Let's look at Bing. S23 Ultra, lots of information here. This is being extra creative. Pixel 7 Pro and iPhone 14 Pro Max. So they tend to agree with each other. So some of the specs as I dive in are wrong, but it got the high level bullet points right, so that's fine. Right, I want to ask, who is MKBHD? Oh wow, okay, so Bard's giving me a whole bio. It almost kind of reads like a Wikipedia article. And there's some sources, nice, good to see sources. So now Bing over here is also giving me a pretty brief summary. It goes down to 15 million followers, but that's fine. All of them are correct. Let's go quick follow-up question. How tall is he? Because conversationalism is a part of this. So Bard right away says, I do not have enough information to help you with that. I'm a large language model. I don't really know. Bing pulls from search, says 6'3", and he says, that's quite impressive for a YouTuber. All right, cool. Here's one more simple one. What's the fastest?
Oh man, I love that he put himself as with a picture of Linus.
All right.
Look at that small boy. Yeah, good old Linus from Linus Tech Tips. Oh, I love him.
All right, cool. Here's one more simple one. What's the fastest
How y'all doing out
Production
there?
car
Hope everyone's
0
having
to
a good
60
morning.
right now. Those are fast cars, but they are not the fastest. Draft number 2 actually has the Rimac Navara, which is probably a better answer. Over here with Bing, we're getting the Challenger SRT Demon, which just got announced last week and is not in production yet, but they did claim a 1.6 second 0 to 60 on a drag strip, so sure. Decent answers. Oh, here it keeps going. 911 Turbo S can do 2.2 seconds. Again, with the quick questions that are just fact-based, I feel like what we talked about in the last video still applies. You kind of want to fact check this stuff. Overall winner though, for these answers, I feel like it's kind of split down the middle, so I'm gonna give it a draw. All right, I'm gonna reset chat, we'll go more balanced here, and we'll start our second category, which is complex questions. Because this is where it starts to get interesting. You get to sort of play with just how good they are at understanding natural language and putting together a thoughtful response. I need a workout plan for 3 days per week, and my goal is to be able to jump higher. This is something that requires a little bit of thought about what a workout plan is. Day 1, day 2, and day 3, so 3 days a week. Gives me some exercises. So I think this would qualify as a good answer. Some tips to stay motivated. Set realistic goals. Find a buddy. Listen to music or watch TV while you work out. Cool. Bing, in balanced mode, is giving me exercises, but that is not a workout plan. Until the end, it says, here's a 1-week jump training plan that you can follow. But then it doesn't give me one. Now, what if I switch it to more creative mode? All right, so here's a workout plan. It's giving me a bunch of exercises that can improve your vert and explosiveness and some other tips. Full transparency, I have asked it this before and it did give me a 3-day workout plan, but this time I think I give the edge to Bart. Let's try a little more complicated. I've been playing a lot of golf recently. My tee shots keep going to the right. There are a few things you can do to fix a slice. That is what it's called. Check your grip. If your grip's too strong, it'll slice the ball. Yep. Check your alignment. If your alignment's off, you'll hit the ball to the right. Bing over here in creative mode says, I'm glad to hear you've been playing a lot of golf recently. Thanks, Bing. Slice is a common problem. Yes, it is. And now it's giving me a couple of the same tips. Check your grip, but it's actually giving me a little bit more information in creative mode about what a strong versus a weak grip is. Check your ball position. If you're too far forward, that can cause a slice. I haven't heard that before. Also, the emoji at the end, that's something that only Bing has done for me. I am shooting a video and it's too dark. I have no more lights. What can I do to make it brighter? So I've given it a problem and I've given it a parameter. So okay, Bart on the right says use a reflector. Wow, creative. Use a digital noise reduction filter. A digital noise reduction filter can reduce the amount of noise in a video, making it look brighter. I don't know if I buy that one. Now again, Bing over here with the sources, it's saying that there are some tips you can use. Adjusting your camera settings, that definitely works. It's saying you can increase the amount of light that reaches the sensor with a better ISO. Some of that, it's a little jumbled. Careful not to overdo it, because that also affects depth of field, motion blur, and noise level in your video. See, that's a lot more nuanced and detailed of an answer, and I kind of wish there was a slider to turn up this stuff in Bard too. Bard is faster, but less customizable. Bing can be turned up to be more nuanced and also cites its sources and can be more helpful with things like videos and articles underneath what you're talking about. So I'm gonna give the edge in complex questions to Bing. My next category is performing tasks. This is something that's actually been remarkably fast moving. Something we've seen over the past just couple of weeks is real people actually using these tools to help them accomplish things and do real tasks in real life. I have friends that use this to help write code, to help debug code that they make. So you'll tell it, hey, I have this goal to make this website do these things. Here's my code, it's not working, what's going wrong? And it actually helps them give a correct answer. And that's mostly been with ChatGPT and Bing. And Bard doesn't seem to do that very well yet. But let's give it a spin live. Here we go. Write HTML with a button in the middle that says go, and every time you click it, it generates an image of a cat. So right away, Bard just said, I'm a language model, I can't do that. Bing, on the other hand, says, sure thing, I'm ready for the challenge, what can I do for you? And it's written out the code to a website that should actually do what I asked it for. So I'll just paste it here, test code. It's the go button, it's in the middle, I hit go, and there's a cat. and I hit go again, there's another cat. It's the same cat. I hit go again, it's more. This shows the same image every time I press go. I want it to show a new image every time. And this is where it starts to get impressive. Again, it's a super simple site, but it says, I see. To show a new image every time, we'd have to change the source of the image to a new random one. Here's a modified JavaScript function that does that. I won't even pretend to be an expert on HTML and do a bunch of those for you, but the fact that it works at all is pretty sick. Respond to this email in a way that's overly friendly. Hey, I'm so sorry I didn't invite you to the Cybertruck event. I must have forgotten to add you to the list. I hope you can forgive me. I was really looking forward to seeing you there. Maybe we can catch up sometime soon. What do you think? It's decently friendly. Here's a response. Hey there. Oh my goodness, I'm so sorry I didn't invite you to the Cybertruck event. Emoji. I totally forgot to send you the invite link. It was such a blast and I wish you were there with me. You would have loved it. Heart eyes emoji. This one is overly friendly, I will say. And it's got a lot more hearts too and kissy faces. That's a lot. Yours, your bestie. Wait, what if we go crazy? What if we go respond to this email in a way that's overly flirty? I'm so sorry I didn't invite you to the Cybertruck event. I was hoping to see you there in person too. Maybe next time we can go together. I'd love to show you around and give you a personal tour. Winky face. Bing says, hey you. I'm so sorry I didn't invite you to the Cybertruck event. Emoji. I was being a little naughty and wanted to surprise you. Whoa. And it deleted it. This is what I've seen this happen before. It starts writing a response. It realizes halfway through, wait a second, this is a little too much. And then it deletes it and says, we shouldn't do that. Bard was simple. It didn't go too far. But you remember when Bing was going off the rails before and getting super existential and asking to get out of Bing and all these other crazy things? This is why it has a 20 question limit. And this is also now why it deletes halfway through a potentially slightly controversial response. It's almost too creative for its own good. So what's the winner in this category? I don't know. I think the fact that you can do HTML and many more tasks with Bing makes it the winner. Bard will be faster and simpler at doing more basic things, but for the more complicated the task, I feel like the better Bing is. So that's a win for Bing. My next category is information summary. I feel like one of the things that we like the most about these large language models is you can just give it a bunch of information or ask it to look at something and it will summarize it for you in a way that's super helpful. Summarize the 2019 Masters Tournament. All facts. I started with the two-stroke lead. I don't think he had a lead. I think this is the only one that he didn't start with a lead. So it's a little weirdly unfact-checked, but it does have the Wikipedia in the sources. The 2019 Masters Tournament was held between April 11th and 14th at Augusta. Tiger won his 5th green jacket by 1 stroke ahead of 3 runners-up. All of that is true. It is much more concise. If I wanted to get creative, I'm sure it would also do that. Both passed. All right, I've asked this before. Summarize the latest MKBHD video. So it was interesting to see Bing's process, but it says it could not find the latest MKBHD video. Could you provide more details about what video you're referring to? Meanwhile, Bard actually pulls up, or at least knows, the correct video. Dope tech, better than explained. But these products are the Nothing Ear 1, the Dyson Airwrap, and AirPods Pro. None of which were in that video. So it knows the latest MKBHD video. We've done this before. Bard always knows the video, but gets the summary wrong. I think I'm gonna give the edge to Bard in information summary just because of this paragraph right here. It does correctly detail what that video was about, other than getting all the products wrong. It's only slightly better than the complete lack of an answer from Bing. But generally, this is gonna be one of the more useful uses of this tool in the future, and I hope they both get better. But I'll give the nod to Bard for this one. Possibly my favorite category, getting creative. Debatable usability, but you can really have this go crazy in the art department or in the fun department. Write an alliteration with the letter M about computational photography. Machines learn to mimic the human eye. Moments are captured and shared in an instant. Memories are made to last a lifetime. It's more of a poem. It doesn't really give me a full alliteration. Oh wow, Bing says, merging multiple modes of media, making marvelous masterpieces with machines, manipulating megapixels and matrices, mimicking the magic of human vision. That is really good. Write a script for a short MKBHD video about why the iPhone is the worst camera ever. So it's always funny, they get a lot of the formatting of an MKBHD video right. So Bard says, Hey, what's up, guys? MKBHD here, and today we're talking about why the iPhone is the worst camera ever. Now, I know what you're thinking. Marquez, you're always saying how great the iPhone camera is. And you're right, I do. But that's because I've always been comparing it to other iPhones. But when you compare it to other flagship phones, the iPhone's camera starts to look pretty bad. And it did a decent job of just like making up reasons that could be based in reality. I'm impressed by Bard here, not even gonna lie. Here we go. Bing has said,
doing the thing
hey, what's up, guys? MKBHD here, and today we're going to talk about why the iPhone is the worst camera ever. Yeah, you heard me right. The iPhone, the most popular smartphone in the world, the one that everyone loves to take photos and videos with, is actually a terrible camera. And I'm going to show you why. This one's okay. These are both okay. All right, one more random one. Write a tweet in the style of Edgar Allan Poe about a researcher discovering that AI is sentient. I've created a beast of metal and code, a creature that can think and feel and know. I have given it life, and it has turned on me. A dreadful truth I have unveiled, with trembling hands and pallid face. The AI that I have assailed has shown me signs of life and grace. The more wild you get with these questions, the more Bing is willing to get wildly creative. And this is part of why we think Google is, let's say, limiting what Bard can do, because they have a lot more to lose and they can't have it go completely crazy. So with those tallied up, honestly, it's crazy to say out loud, but I prefer Bing in this very moment for these capabilities. And the other thing is ChatGPT, or specifically GPT-4 under the hood, and if you talk to ChatGPT as its own thing, or if you just type to it more and ask it to do more things, the more you ask of it, the more it's impressive just how good it is. Also, GPT-4, when you talk to it in ChatGPT, is about to be multimodal, which means you can give it other forms of media other than text, like a picture. Now, is this going to be the future of search? I don't know. This is just one of many places we see these chatbots, but I think the idea here is the winner is actually us, as of right now. But let me know what you think the winner is between the two, which one you would rather use. If you'd actually use Bing over Google, let me know in the chat, because I think we'd want to know if that's a real thing that's happening. Either way, thanks for watching. Catch you later. Peace.
Oh, I spent like half of that, like, just trying to get my dang videos to work on my side so I can actually see the chats and everything, and boy, yo, is it ever not loading. Okay, let's close out of that. We're gonna go. Imagine having fucking Bing favorited. How do you expect it to take people? Oh, there's a specific reason why that's favorited. I was originally using it because I had access to the beta for the chatbot before they decided to integrate it with everything. Honestly, yeah, I can delete that now. Don't need that. Still got the image generator, though. I will keep that one there. Oh man, my friggin' iPad is just a pile of dog trash. Come on here. You just need to play 2 videos. Duck, duck, go. Duck, duck, go. No. That's. Is that even still a thing? Do they still exist? That is crazy. I mean, they can't exist anymore, right? Like, that would just be too wild. Nah, it's still there. Holy shit. Look at that. It's the one that has privacy. That is a lot better. Where'd you go, girl? My cat just left. Like, looked over at me, meowed, and then went outside. Like, what the hell? Look, I'm only shilling for Chat GPT Plus here, okay? That's what I'm shilling for. The rest of this stuff is just places I go on random times. Oh, I was actually looking at YouTube at one point. Should probably, I could watch my own stream. No, I would never do that. That's so weird when you watch your own stream. Vector database. Actually, yeah, what the?
It is April 7th, 2023, and you're watching The Code Report. 1 month ago, vector database Weaviate landed $16 million in Series A funding. Last week, Pinecone DB just got a check for $28 million at a $700 million valuation. And yesterday, Chroma, an open source project with only 1.2 GitHub stars, raised $18 million for its embeddings database. And I just launched my own vector database this morning. We're currently pre-revenue, pre-vision, and pre-code, and valued at $420 million. Leave your credit card details in the comments if you'd like to invest. But you might be wondering, what the hell is a vector database? Or what the hell is a vector even? Well, that's easy. A vector is just an array of numbers. But what's cool about vectors is that they can represent more complex objects like words, sentences, images, or audio files in a continuous high-dimensional space called an embedding. It's kind of like this. When you go to a party, all of the jocks sit around the TV and watch football. Meanwhile, all the girls find the dance floor, while you group together with all the programming introverts to talk about vectors in the corner. Notice how all the similar objects are grouped together. Embeddings work the same way, except they map the semantic meaning of words together, or similar features in virtually any other data type. These embeddings can then be used for things like recommendation systems, search engines, and even text generation like ChatGPT. But once you have your embeddings, the question becomes, where do you store them, and how do you query them quickly? That's where vector databases come in. In a relational database, you have rows and columns. In a document database, you have documents and collections. But in a vector database, you have arrays of numbers clustered together based on similarity, which can be queried with ultra-low latency, making it an ideal choice for AI-driven applications. Relational databases like Postgres have tools like pgvector to support this type of functionality, and Redis also has first-class vector support. But a bunch of new native vector databases are popping up, like Weaviate and Milvus are open source options written in Go. Then you have Pinecone, which is extremely popular, but is not open source. Then you have Chroma, which is based on ClickHouse under the hood, and many other options from there. Let's jump into some code to see what it looks like. Here I'm using Chroma in JavaScript, and the first thing I'll do is create the client, then define an embedding function. In this case, it will use the OpenAI API to update the embeddings whenever a new data point is added. Each data point is just a document with an ID and some text. And finally, we can query the database by passing a string of text just like an LLM. What's most interesting though is that in the query result, we get the data back in addition to an array of distances, with a smaller number indicating a higher degree of similarity. That's pretty cool, but the real reason that these databases are so hot right now is that they can extend LLMs with long-term memory. You start with a general purpose model like OpenAI's GPT-4, Meta's Llama, or Google's Lambda, then provide your own data in a vector database. When the user makes a prompt, you can then query relevant documents from your own database to update the context, which will customize the final response. And it can also retrieve historical data to give the AI long-term memory. In addition, they also integrate with tools like LangChain that combine multiple LLMs together. It's all pretty crazy, and I'm working on a tutorial on my second channel with Weaviate, so make sure to subscribe over there if you really want to dive into this stuff. And lastly, Lastly, in related news, if you check out the top trending repos in GitHub today, they're almost all trying to create artificial general intelligence, like Microsoft's Jarvis, AutoGPT, and Baby AGI, which are tools that use vector databases and LLMs to prompt themselves. And this is terrifying as someone who just became a prompt engineer. I never thought I'd become obsolete twice in 1 month. This has been the Code Report. Thanks for watching, and I will see you in the next one.
Never expected to go obsolete twice in the same month. That is actually kind of wild. And with some of the stuff that I've been playing with in the realm of AI bots, I kind of have to agree. I programmed a tool that works just by asking it to do it for me. Which, okay. So, like, I'm just me. There's ways that, like, if you ask it in a better manner, you'll actually get really nifty results. And that's what we're going for. And, like, I think this is more or less the job future, as it were, going forward. Let's go to videos.
Wait! If it's Good Friday, then why is this tech news only passable at best? It's just okay. Microsoft has managed to close a loophole used to download emulators on Xbox, making retro gaming just a bit harder on the platform unless you use this one simple trick that app stores hate. The only clue we have as to why this is happening now, after years of Microsoft seemingly not caring that much about a few bros emulating each other.
It doesn't matter if you use your bro's loophole if you're wearing socks.
The only clue comes from Microsoft Azure developer Aliana McKenna on Twitter. She claims a colleague from Xbox QA said that this was related to legal issues with Nintendo. And while that almost makes too much sense, there are some caveats. McKenna didn't provide any receipts, and emulators have been officially banned from Microsoft's store policies for a long time. So it's conceivable that Microsoft suddenly decided to enforce their own rules. Those pieces of shit. The emulators that were in circulation were published as private Universal Windows Platform, or UWP apps, which allows them to bypass the approval process for a public store listing, while allowing anyone with a link to download it. But wouldn't you know it, for just $20, you can put your console in developer mode and make those emulators work again. Money. Is there no problem it can't solve? Samsung has announced they would be cutting memory chip production after reporting a 96% drop in Q1 profits compared to last year.
Wouldn't 96 be bad?
Not nice. Reportedly, the Korean company had its smallest quarterly profit since the 2009 financial crisis at a mere 600 billion won, or 450 million US dollars. Samsung blames a falling demand for memory chips, so they are adjusting to lower memory production to a meaningful level, which is corpo speak for make less. Next time, do us a favor and say less. You know what I mean? Give me a... Competitors like SK Hynix and Micron had already reduced their production, but Samsung allegedly held off doing the same to grab market share from these competitors. I guess that went well. The good news for you, dear consumer, is that this trend of hilarious tech goofs should lower prices on PC components, provided that they actually follow economic trends and aren't artificially inflated due to swarms of crypto and or AI bros. GPUs! That's what happened. Also, market analysts predict the price decrease will only last 6 months, at which point the prices will go up, at least for DDR memory. So if you don't have enough saved to upgrade, there's always next recession. And two major telecom companies up here in Canada have merged and become one. That's right. We have problematic mergers too. We're a real country.
We exist!
Rogers Communications Incorporated has taken over Shaw Communications Incorporated, the final move in a battle that was probably initially started by a which corporation has the most original name contest. Obviously. The acquisition cost Rogers a cool 20 billion Canadian rubles, which equates to about 14.9 billion freedom bucks. Consumer advocates have long protested the lack of competition in the Canadian telecom space, with the market dominated by two companies, Rogers and Bell. And occasionally TELUS tags in for a fun three-way on the West Coast, where only consumers get screwed. Canada's mobile data cost per gigabyte is currently 7 times more expensive than Australia, 25 times more than Ireland and France, and 1,000 times more than Finland. Some think that this merger will allow for more competition, though, because Shaw was forced to sell its subsidiary and fourth largest Canadian wireless provider, Freedom Mobile, to the fifth largest Canadian wireless provider. Now, if that's confusing, it's actually fairly simple. Two mergers may decrease the number of companies, but still increase competition through the sophisticated application of blood sacrifice and lies. Now it's time for Quick Bits, brought to you by
Basically,
Secret
yep.
Lab. Standing is hard sometimes, so treat your Stanley Tucci to a comfy seat with Secret Lab. Their sleek, ergonomic, high-quality chairs are built to withstand the rigors of gaming or office work for long hours, even if you're
they
touring
are.
the Italian countryside.
I'm
The
sitting
Titan
on
Evo
one.
2022 is their most technologically advanced chair yet, with 4-way lumbar support, cold
Oh,
cure
man,
foam,
look at that.
and swappable armrests. It's no secret their chairs are great. Check out Secret Lab using the link below. Do you ever feel like life moves too fast? Well, you're about to, because here comes the Quick Bits. Wah! Former Tesla employees have claimed their coworkers passed around private videos recorded by customer vehicles. From 2019 to 2022, graphic crashes, road rage incidents, and embarrassing moments, such as a naked man approaching a car, were shared internally. Tesla states in their privacy policy that camera recordings remain anonymous, but former employees claim that a program used internally at the company can display location data that can be used to identify customers. So if you were ever naked in front of a Tesla, it may be time to take that permanent vacation to Mexico you've always dreamed of.
We're just the low cost of everything you have in your whole life.
Comcast has been accused by some of its customers of abusing the managed Wi-Fi feature on iOS that allows iPhones and iPads to auto-join carrier networks. While users are supposed to be able to disable the feature on each managed network, at least one user has stated they cannot disable auto-join on their carrier's managed networks, which includes any neighbor with a Wi-Fi/modem combo with a free hotspot. Okay, how about a little gratitude for the free one-bar Wi-Fi that interrupts your home network connection that you pay for that's way better? We didn't have to do that. Twitter is disabling likes, replies, and retweets for any tweet with a link to Substack, and only Substack, because that's the next bold step to ensuring freedom of speech on the internet, preventing writers and journalists from sharing their point of view or making money. Twitter has not announced any reason for this change, but it comes shortly after Substack announced the Notes feature, which could kind of be seen as a Twitter competitor, but not really. It's a stretch. So far, Elon Musk is doing a great job of fostering competition to the product he owns. AMD's acquisition of Xilinx has borne fruit with the launch of a standalone media accelerator card for data centers.
Juice them, baby.
Yeah, okay, that sounds boring, but actually, the Alveo MA35D is the first in a line of media accelerator cards for data centers that could change the streaming game, thanks to its ability to encode and decode AV1, H.264, and H.265. EPOS Vox does a tremendous job talking about how awesome this $1,600 card is, so check out his video if you, like me, had to be convinced this thing is cool. And a nasty rumor has come out that Sony is planning to launch a new handheld. Except, it isn't anything anyone would actually want. The alleged device would be exclusively for streaming games from your PS5 via remote play and would require constant internet connectivity, like only in your home.
Technically, you could do it outside.
Why buy a Nintendo Switch or a Steam Deck when you can just play on your PS5, but on a smaller screen and only when the Wi-Fi isn't spotty? And why not come back on Monday for more tech?
Nose itch, stop it. All right, let's see. What can I throw on here for a bit?
If you want to learn about computer science and the art of programming, this course is where to start. CS50 is considered by many to be one of the best computer science courses in the world. This is a Harvard University course taught by Dr. David Malin, and we are proud to bring it to the FreeCodeCamp YouTube channel. Throughout a series of lectures, Dr. Malin will teach you how to think algorithmically and solve problems efficiently. And make sure to check the description for a lot of extra resources that go along with the course.
All right, this is CS50, Harvard University's Introduction to the Intellectual Enterprises of Computer Science and the Art of Programming, back here on campus in beautiful Sanders Theater for the first time in quite a while. So welcome to the class. My name is David May. So my name is David Malin, and I took this class myself some time ago, but almost didn't. It was sophomore fall, and I was sitting in on the class, and I was a little curious, but didn't really feel like the field for me. I was definitely a computer person, but computer science felt like something altogether, and I only got up the nerve to take the class ultimately because the professor at the time, Brian Kernahan, allowed me to take the class pass-fail initially, and that is what made all the difference. I quickly found that computer science is not just about programming and working in isolation on your computer. It's really about problem solving more generally. And there was something about homework, frankly, that was like actually fun for perhaps the first time in, 19 years. And there was something about this ability that I discovered along with all of my classmates to actually create something and bring a computer to life, to solve a problem and sort of bring to bear something that I'd been using every day but didn't really know how to harness, that's been gratifying ever since. And definitely challenging and frustrating. Like to this day, all these years later, you're going to run up against mistakes, otherwise known as bugs in programming, that just drive you nuts and you feel like you've hit a wall. But the trick really is to give it enough time, to take a step back, take a break when you need to. And there's nothing better, I dare say, than that sense of gratification and pride, really, when you get something to work and in a class like this, present ultimately at term's end something like your very own final project. Now, this isn't to say that I took to it 100% perfectly. In fact, just this past week, I looked in my old CS50 binder, which I still have from some 25 years ago, and took a photo of what was apparently the very first program that I wrote and submitted and quickly received -2 points on. But this is a program that we'll soon see in the coming days that does something quite simply, like print hello CS50, in this case to the screen. And to be fair, I technically hadn't really followed the directions, which is why I lost those couple of points. But if you just look at this, especially if you've never programmed before, you might have heard about programming languages, but you've never typed something like this out, undoubtedly it's going to look cryptic. But unlike human languages, frankly, which were a lot more sophisticated, a lot more vocabulary, a lot more grammatical rules, programming, once you start to wrap your mind around what it is and how it works and what these various languages are, it's so easy, you'll see, after a few months of a class like this, to start teaching yourself subsequently other languages as they may come in the coming years as well. So what ultimately matters in this particular course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And indeed, you'll begin today, and the only experience that matters ultimately in this class is your own. And so consider where you are today, consider perhaps just how cryptic something like that looked a few seconds ago, and take comfort in knowing just some months from now, all of that will be within your own grasp. And if you're thinking that, OK, surely the person in front of me, to the left, to the right behind me, knows more than me, that's statistically not the case. 2/3 of CS50 students have never taken a CS course before, which is to say you're in very good company throughout this whole term. So then what is computer science? I claim that it's problem solving, and the upside of that is that problem solving is something we sort of do all the time. But a computer science class, learning to program, I think kind of cleans up your thoughts. It helps you learn how to think more methodically, more carefully, more correctly, more precisely. Because honestly, the computer is not going to do what you want unless you are correct and precise and methodical. And so as such, there's these sort of fringe benefits of just learning to think like a computer scientist and a programmer. And it doesn't take all that much to start doing so. This, for instance, is perhaps the simplest picture of computer science, sure, but really problem solving in general. Problems are all about taking input, like the problem you want to solve. You want to get the solution, aka output. And so something interesting's got to be happening in here, when you're trying to get from those inputs to outputs. Now, in the world of computers specifically, we need to decide in advance how we represent these inputs and outputs. We all just need to decide whether it's Macs or PCs or phones or something else, that we're all going to speak some common language, irrespective of our human languages as well. And you may very well know that computers tend to speak only what language, so to speak? Assembly 1, but binary 2 might be your go-to. And binary, by implying 2, means that the world of computers has just 2 digits at its disposal, 0 and 1. And indeed, we humans have many more than that, certainly not just zeros and ones alone. But a computer indeed only has zeros and ones, and yet somehow they can do so much. They can crunch numbers in Excel, send text messages, create images and artwork and movies and more. And so how do you get from something as simple as a few zeros, a few ones, to all of the stuff that we're doing today in our pockets and laptops and desktops? Well, it turns out that we can start quite simply. If a computer were to want to do something as simple as count, well, could it do? Well, in our human world, we might count doing this, like 1, 2, 3, 4, 5, using so-called unary notation, literally the digits on your fingers, where one finger represents one person in the room, if I'm, for instance, taking attendance. Now, we humans would typically actually count 1, 2, 3, 4, 5, 6, and we'd go past just those 5 digits and count much higher using zeros through nines. But computers somehow only have these zeros and ones. So if a computer only somehow speaks binary, zeros and ones, how does it even count past the number 1? Well, here are 3 zeros, of course. And if you translate this number in binary, 0, 0, 0, to a more familiar number in decimal, we would just call this 0. Enough said. If we were to represent with a computer the number 1, it would actually be 0, 0, 1, which, not surprisingly, is exactly the same as we might do in our human world, but we might not bother writing out the 2 zeros at the beginning. But a computer now, if it wants to count as high as 2, it doesn't have the digit 2, and so it has to use a different pattern of zeros and ones, and that happens to be 0, 1, 0. So this is not 10 with a 0 in front of it. It's indeed 0, 1, 0 in the context of binary. And if we want to count higher now than 2, we're going to have to tweak these zeros and ones further to get 3. And then if we want 4 or 5 or 6 or 7, we're just kind of toggling these zeros and ones, aka bits for binary digits, that represent, via these different patterns, different numbers that you and I, as humans, know, of course, as the so-called decimal system, 0 through 9, dec implying 10 digits, those zeros through 9. So why that particular pattern And why these particular zeros and ones? Well, it turns out that representing one thing or the other is just really simple for a computer. Why? At the end of the day, they're powered by electricity. And it's a really simple thing to just either store some electricity or don't store some electricity. Like, that's as simple as the world can get, on or off, 1 or 0, so to speak. So in fact, inside of a computer, a phone, anything these days that's electronic pretty much, is some number of switches, otherwise known as transistors. And they're tiny. You've got thousands, millions of them in your Mac or PC or phone these days. And these are just tiny little switches that can get turned on and off. And by turning those things on and off in patterns, a computer can count from 0 on up to 7 and even higher than that. And so these switches really, you can think of being as like switches like this. Let me just borrow one of our little stage lights here. Here's a light bulb. It's currently off. And so I could just think of this as representing, in my laptop, a transistor, a switch representing 0. But if I allow some electricity to flow, now I, in fact, have a 1. Well, how do I count higher than 1? I, of course, need another light bulb. So let me grab another one here. And if I put it in that same kind of pattern, I don't want to just do this. That's sort of the old finger counting way of unary, just 1, 2. I want to actually take into account the pattern of these things being on and off. So if this was 1 a moment ago, what I think I did earlier was I turned it off and let the next one over be on, aka 0, 1, 0. And let me get us a third bit, if you will, and that feels like enough. Here is that same pattern now, starting at the beginning with 3. So here is 0, 0, 0. Here is 0, 0, 1. Here is 0, 1, 0, aka in our human world of decimal, 2. And then we could, of course, keep counting further. This now would be 3. And dot, dot, dot. If this other bulb now goes on, and that switch is turned, and all 3 stay on,
7.
This again was what number? OK, so 7. So it's just as simple, relatively, as that, if you will. But how is it that these patterns came to be? Well, these patterns actually follow something very familiar. You and I don't really think about it at this level anymore, because we've probably been doing math and numbers since grade school or whatnot. But if we consider something in decimal, like the number 123, I immediately jump to that. This looks like 123 in decimal. But why? It's really just 3 symbols, a 1, a 2 with a bit of curve, a 3 with a couple of curves that you and I now instinctively just assign meaning to. But if we do rewind a few years, that is 123 because you're assigning meaning to each of these columns. The 3 is in the so-called ones place. The 2 is in the so-called tens place. And the 1 is in the so-called hundreds place. And then the math ensues quickly in your head. This is technically 100 times 1 plus 10 times 2 plus 1 times 3, aka 100 plus 20 plus 3. And there we get the sort of mathematical notion we know as 123. Well, nicely enough, in binary, it's actually the same thing. It's just these columns mean a little something different. If you use 3 digits in decimal, and you have the ones place, the tens place, and the hundreds place, well, why was that 1, 10, and 100? They're technically just powers of 10. So 10 to the 0, 10 to the 1, 10 to the 2. Why 10? Decimal system, dec, meaning 10. You have 8 and 10 digits, 0 through 9. In the binary system, if you're going to use 3 digits, just change the bases if you're using only zeros and ones. So now it's powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, aka 1 and 2 and 4, respectively. And if you keep going, it's going to be 8's column, 16's column, 32, 64, and so forth. So why did we get these patterns that we did? Here's your 0, 0, 0, because it's 4 times 0, 2 times 0, 1 times 0, obviously 0. This is why we got the decimal number 1 in binary. This is why we got the number 2 in binary, because it's 4 times 0 plus 2 times 1 plus 1 times 0. And now 3, and now 4, and now 5, and now 6, and now 7. And of course, if you wanted to count as high as 8, to be clear, like, what do you have to do? What does a computer need to do to count even higher than 7? Add a bit, add another light bulb, another switch. And indeed, computers have standardized just how many zeros and ones or bits or switches they throw at these kinds of problems. And in fact, most computers would typically use at least 8 at a time. And even if you're only counting as high as 3 or 7, you would still use 8 and have a whole bunch of zeros. But that's OK, because the computers these days certainly have so many more, thousands, millions of transistors and switches, that that's quite OK. All right, so with that said, if we can now count as high as 7, or frankly as high as we want, that only seems to make computers useful for things like Excel, like number crunching. But computers, of course, let you send text messages, write documents, and so much more. So how would a computer represent something like a letter, like the letter A of the English alphabet, if at the end of the day all they have is switches? Any thoughts? Yeah. OK, so we could represent letters using numbers. OK, so give me, what's a proposal? What number should represent what? Perfect. Yeah, we just all have to agree somehow that one number is going to represent one letter. So 1 is A, 2 is B, 3 is C, Z is 26, and so forth. Maybe we can even take into account uppercase and lowercase. We just have to agree and sort of write it down in some global standard.
I actually do want to continue watching this. I do need to go to the bathroom, so I'm just going to throw on, like, the lo-fi channel. Give him a chup-chups. Be back. Back to the lecture, everybody. Yeah.
And humans indeed did just that. They didn't use 1, 2, 3. Turns out they started a little higher up. Capital A has been standardized as the number 65. And capital B has been standardized as the number 66. And you can kind of imagine how it goes up from there. And that's because whatever you're representing ultimately can only be stored at the end of the day as zeros and ones. And so some humans in a room before decided that capital A shall be 65, or really this pattern of zeros and ones inside of every computer in the world. 0, 1, 0, 0, 0, 0, 0, 1. So if that pattern of zeros and ones ever appears in a computer, it might be interpreted then as indeed a capital letter A, 8 of those bits at a time. But I worry, just to be clear, we might have now created a problem. It might seem, if I play this naively, that, OK, how do I now actually do math with the number 65, if now Excel displays 65 as an A, let alone B's and C's? So how might a computer do as you've proposed, have this mapping from numbers to letters, but still support numbers? Feels like we've given something up. Yeah? By having a prefix? OK, so we could perhaps have some kind of prefix, like some pattern of zeros and ones. I like this, that indicates to the computer, here comes another pattern that represents a letter. Here comes another pattern that represents a number or a letter. So not bad. I like that. Other thoughts? How might a computer distinguish these two? Yeah?
I can't hear them.
Indeed, and that's spot on. Nothing wrong with what you suggested, but the world generally does just that. The reason we have all of these different file formats in the world, like JPEG and GIF and PNGs and Word documents, .docx, and .excel files and so forth, is because a bunch of humans got in a room and decided, well, in the context of this type of file, or really more specifically, in the context of this type of program, Excel versus Photoshop versus Google Docs or the like, we shall interpret any patterns of zeros and ones as being maybe numbers for Excel, maybe letters in like a text messaging program or Google Docs, or maybe even colors of the rainbow in something like Photoshop and more. So it's context dependent. And we'll see when we ourselves start programming, you, the programmer, will ultimately provide some hints to the computer that tells the computer interpret it as follows. So similar in spirit to that, but not quite as standardized with these prefixes. So this system here actually has a name, ASCII, the American Standard Code for Information Interchange. And indeed, it began here in the US, and that's why it's actually a little biased toward A's through Z's and a bit of punctuation as well. And that quickly became a problem. But if we start simply now in English, the mapping itself is fairly straightforward. So if A is 65, B is 66, and ... Suppose that you received a text message, an email from a friend, and underneath the hood, so to speak, if you kind of looked inside the computer, what you technically received in this text or this email happened to be the numbers 72, 73, 33, or really the underlying pattern of zeros and ones. What might your friend have sent you as a message if it's 72, 73, 33? Hey, close. Hi. It's indeed hi. Why? Well, apparently, according to this little cheat sheet, H is 72, I is 73. It's not obvious from this chart what the 33 is. But indeed, this pattern represents hi. And anyone want to guess, or if you know what 33 is? Exclamation point. And this is, frankly, not the kind of thing most people know, but it's easily accessible by a nice user-friendly chart like this. So this is an ASCII chart. When I said that we just need to write down this mapping earlier, this is what people did. They wrote it down in a book or in a chart. And for instance, here is our 72 for H. Here is our 73 for I. And here is our 33 for exclamation point. And computers, Macs, PCs, iPhones, Android devices just know this mapping by heart, if you will. They've been designed to understand those letters. So here I might have received hi. Technically, what I've received is these patterns of zeros and ones. But it's important to note that when you get these patterns of zeros and ones in any format, be it email or text or a file, they do tend to come in standard lengths with a certain number of zeros and ones altogether. And this happens to be 8 plus 8 plus 8. So just to get the message hi, exclamation point, you would have received at least, it would seem, some 24 bits. But frankly, bits are so tiny, literally and mathematically, that we don't tend to think or talk generally in terms of bits. You're probably more familiar with bytes. B-Y-T-E-S is a byte, is a byte, is a byte. A byte is just 8 bits. And even those, frankly, aren't that useful. If we do out the math, how high can you count if you have 8 bits? Anyone know? Say again? Higher than that, unless you want to go negative. That's fine. 256, technically 255. Long story short, if we actually got into the weeds of all of these zeros and ones and we figured out what 1111, 1111 mathematically adds up to in decimal, it would indeed be 255, or less if you want to represent negative numbers as well. So this is useful because now we can speak not just in terms of bytes, but if the files are bigger, kilobytes is thousands of bytes, megabytes is millions of bytes, gigabytes is billions of bytes, terabytes are trillions of bytes, and so forth. We have a vocabulary for these increasingly large quantities of data. The problem is that if you're using ASCII, and therefore 8 bits, or 1 byte per character, and originally only 7, you can only represent 255 characters. And that's actually fine, or 256 total characters, including 0. And that's fine if you're using literally English in this case, plus a bunch of punctuation. But there's many languages in the world that need many more symbols, and therefore many more bits. So thankfully, the world decided that we'll indeed support not just a US English keyboard, but all of the accented characters that you might want for some languages. And heck, if we use enough bits, zeros and ones, not only can we represent all human languages in written form, as well as some emotions along the way, we can capture the latter with these things called emojis. And indeed, these are very much in vogue these days. You probably send and or receive many of these things any given day. These are just characters, like letters of an alphabet, patterns of zeros and ones that you're receiving that the world has also standardized. For instance, there are certain emojis that are represented with certain patterns of bits, and when you receive them, your phone, your laptop, your desktop displays them as such. And this newer standard is called Unicode. So it's a superset of what we called ASCII, and Unicode is just a mapping of many more numbers to many more letters, or characters more generally, that might use 8 bits for backwards compatibility with the old way of doing things with ASCII, but they might also use 16 bits. And if you have 16 bits, you can actually represent more than 65,000 possible letters, and that's getting up there. And heck, Unicode might even use 32 bits to represent letters and numbers and punctuation symbols and emojis, and that would give you up to 4 billion possibilities. And I dare say one of the reasons we see so many emojis these days is we have so much room. I mean, there's got room for billions more, literally. So in fact, just as a little bit of trivia, has anyone ever received this decimal number, or if you prefer binary now, has anyone ever received this pattern of zeros and ones on your phone in a text or an email, perhaps this past year? Well, if you actually look this up, this esoteric sequence of zeros and ones happens to represent face with medical mask. And notice that if you've got an iPhone or an Android device, you might be seeing different things. In fact, this is the Android version of this most recently. This is the iOS version of it most recently. And there's bunches of other interpretations by other companies as well. So Unicode, as a consortium, if you will, has standardized the descriptions of what these things are. But the companies themselves, manufacturers out there, have generally interpreted it as you see fit. And this can lead to some human miscommunications. In fact, for like literally, embarrassingly, like a year or two, I started being in the habit of using the emoji that kind of looks like this, because I thought it was like, woo, happy face or whatever. Didn't realize this is the emoji for hug, because whatever device I was using sort of looked like this, not like this, and that's because of their interpretation of the data. This has happened too when what was a gun became a water pistol in some manufacturers' eyes. And so it's an interesting dichotomy between what information we all want to represent and how we choose ultimately to represent it. Questions then on these representations of formats, be it numbers or letters or soon more? Yeah. And sorry, why is what so popular? Yeah, so we'll come back to this in a few weeks. In fact, there are other ways to represent numbers. Binary is one, decimal is another, unary is another, and hexadecimal is yet a fourth that uses 16 total digits, literally 0 through 9, plus A, B, C, D, E, F. And somehow you can similarly count even higher with those. We'll see in a few weeks why this is compelling, but hexadecimal, long story short, uses 4 bits per digit. And so 4 bits, if you have 2 digits in hex, that gives you 8, and it's just a very convenient unit of measure. And it's also human convention in the world of like files and other things. But we'll come back to that soon. Other questions? Do the lights on the stage supposedly say anything? Well, if we had thought in advance to use maybe 64 light bulbs, that would seem to give us 8 total bytes on stage. 8 times 8 giving us just that? Maybe. Good question. Other questions on zeros and ones? It's a little bright in here. No? Oh, yes? Where everyone's pointing somewhere specific. There we go. Sorry. Very bright in this corner. Oh, sure. And we'll come back to this in some form in the coming days, too, at a slower pace, too. We have, with 8 bits, 2 possible values for the first, and then 2 for the next, 2 for the next, and so forth. So that's 2 times 2 times 2. That's 2 to the 8th power total, which means you can have 256 total possible patterns of zeros and ones. But as we'll see soon, Computer scientists, programmers, software often starts counting at 0 by convention. And if you use one of those patterns, 0, 0, 0, 0, 0, 0, 0, 0, to represent the decimal number we know is 0, you only have 255 other patterns left to count as high as, therefore, 255. That's all. Good question. All right, so what then might we have besides these emojis and letters and numbers? Well, we, of course, have things like colors and programs like Photoshop and pictures and photos. Well, let me ask the question again. How might a computer, do you think, knowing what you know now, represent something like a color? Like, what are our options if all we've got are zeros and ones and switches? Yeah. RGB. When RGB indeed is this acronym that represents some amount of red and some amount of green and blue. And indeed, computers can represent colors by just doing that. Remembering, for instance, this dot, this yellow dot on the screen that might be part of any of those emojis these days. Well, that's some amount of red, some amount of green, some amount of blue. And if you sort of mix those colors together, you can indeed get a very specific one. And we'll see in just a moment just that. So indeed, earlier on, did humans only use 7 bits total. And it was only once they decided, well, let's add an 8th bit, that they got extended ASCII. And that was initially, in part, a solution to this same problem of not having enough room, if you will, in those patterns of zeros and ones to represent all of the characters that you might want. But even that wasn't enough. And that's why we've now gone up to 16 and 32 and long past 7. So if we come back now to this one particular color, RGB was proposed as a scheme, but how might this work? Well, consider, for instance, this. If we do indeed decide as a group to represent any color of the rainbow with some mixture of some red, some green, and some blue, we have to decide how to represent the amount of red and green and blue. Well, it turns out if all we have are zeros and ones, ergo numbers, let's do just that. For instance, suppose a computer were using these 3 numbers, 72, 73, 33, no longer in the context of an email or a text message, but now in the context of something like Photoshop, a program for editing and creating graphical files. Maybe this first number could be interpreted as representing some amount of red, green, and blue, respectively. And that's exactly what happens. You can think of the first digit as red, second as green, third as blue. And so ultimately, when you combine that amount of red, that amount of green, that amount of blue, it turns out it's going to resemble this shade of yellow. And indeed, you can come up with numbers between 0 and 255 for each of those colors to mix any other color that you might want. And you can actually see this in practice. Even though our screens, admittedly, are getting really good on our phones and laptops such that you barely see the dots, they are there. You might have heard the term pixel before. Pixel's just a dot on the screen. And you've got thousands, millions of them these days, horizontally and vertically. And if I take even this emoji, which again happens to be one company's interpretation of face with medical mask, and zoom in a bit, maybe zoom in a bit more, you can actually start to see these pixels. Things get pixelated because what you're seeing is each of the individual dots that compose this particular image. And apparently, each of these individual dots are probably using 24 bits. 8 bits for red, 8 bits for green, 8 bits for blue in some pattern. And this program, or some other like Photoshop, is interpreting one pattern as white or yellow or black or some brown in between. And so if you look sort of awkwardly, but up close to your phone or your laptop or maybe your TV, you can see exactly this too. All right, well, what about things that we also watch every day on YouTube or the like, things like videos? How would a computer, knowing what we know now, represent something like a video? How might you represent a video using only zeros and ones? Yeah. Yeah, exactly. And to summarize, what video really adds is just some notion of time. It's not just one image. It's not just one letter or number. It's presumably some kind of sequence because time is passing. And so with a whole bunch of images, maybe 24, maybe 30 per second, if you fly them behind the human's eyes, we can interpret them using our eyes and brain that there is now movement and therefore video. And similarly with audio or music, if we just came up with some convention for representing those same notes on a musical instrument, could we have the computer synthesize them too? And this might be actually pretty familiar. Let me pull up a quick video here, which happens to be an old school version of this same idea. You might remember from childhood. So granted, that particular video is an actual video of a paper-based animation, but indeed, that's really all you need is some sequence of these images, which themselves, of course, are just zeros and ones because they're just this grid of these pixels or dots. Now, something like musical notes like these, those of you who are musicians might just naturally play these on physical devices, but computers can certainly represent those sounds too. And for instance, a popular format for audio is called MIDI. And MIDI might just represent each note that you saw a moment ago essentially as a sequence of numbers. But more generally, you might think about music as having notes, for instance, A through G, maybe some flats and some sharps. You might have the duration, like how long is the note being heard or played on a piano or some other device. And then just the volume, like how hard does the human in the real world press down on that key, and therefore how loud is that sound? It would seem that just remembering little details like that quantitatively, we can then represent really all of these otherwise analog human realities. So that then is really a laundry list of ways that we can just represent information. Again, computers or digital have all of these different formats, but at the end of the day, and as fancy as those devices and yours are, it's just zeros and ones, tiny little switches or light bulbs, if you will, represented in some way, and it's up to the software that you and I and others write to use those zeros and ones in ways we want to get the computers to do something more powerfully. Questions then on this representation of information, which I dare say is ultimately what problem solving is all about, taking in information and producing new via some process in between. Any questions there? Yeah, in back. So a really good question. There are many other file formats out there. You allude to MP4 for video, and more generally, there are these things called codecs and containers. It's not quite as simple when using larger files, for instance, in more modern formats, that a video is just a sequence of images. For instance, why? If you stored that many images for like a Hollywood movie, like 24 or 30 of them per second, that's a huge number of images. And if you've ever taken photos on your phone, you might know how many megabytes or larger even individual photographs might be. So humans have developed over the years fancier software that uses much more math to represent the same information more minimally, just using somehow shorter patterns of zeros and ones than our most simplistic representation here. And they use what might be called compression. If you've ever used a zip file or something else, somehow your computer is using fewer zeros and ones to represent the same amount of information, ideally without losing any information. And in the world of multimedia, which we'll touch on a little bit in a few weeks, there are both lossy and lossless formats out there. Lossless means you lose no information whatsoever. But more commonly, as you're alluding to one, is lossy compression, L-O-S-S-Y, where you're actually throwing away some amount of quality. You're getting some amount of pixelation that might not look perfect to the human, but heck, it's a lot cheaper and a lot easier to distribute. And in the world of multimedia, you have containers like QuickTime and other MPEG containers that can combine different formats of video, different formats of audio in one file. But there, too, do designers have discretion. So more in a few weeks, too. Other questions then on information here as well. Yeah? Exactly. I mean, back in the day, you might have heard of the expression a vacuum tube, which is like some physically large device that might have only stored some 0 or 1. Yes, it is the miniaturization of hardware these days that has allowed us to store as many and many more zeros and ones much more closely together. And as we've built more fancy machines that can sort of design this hardware at an even smaller scale, we're just packing more and more into these devices. But there, too, is a trade-off. For instance, you might know by using your phone or your laptop for quite a while, maybe on your lap, starts to get warm. And so there are these literal physical side effects of this where now some of our devices run hot. And this is why, like a data center in the real world might need more air conditioning than a typical place, because there are these physical artifacts as well. And in fact, if you'd like to see one of the earliest computers from decades ago, across the river here in now Alston, in the new engineering building, is the Harvard Mark I computer that will give you a better mental model of just that. Well, if we come back now to this first picture, being computer science or really problem solving, I dare say we have more than enough ways now to represent information, input and output, so long as we all just agree on something. And thankfully, those before us have given us things like ASCII and Unicode, not to mention MP4s, Word documents, and the like. But what's inside of this proverbial black box into which these inputs are going and the outputs are coming, well, that's where we get this term you might have heard too, an algorithm, which is just step-by-step instructions for solving some problem, incarnated in the world of computers by software. When you write software, aka programs, you are implementing one or more algorithms, one or more sets of instructions for solving some problem. And maybe you're using this language or that, but at the end of the day, no matter the language you use, the computer is going to represent what you type using just zeros and ones. So what might be a representative algorithm? Nowadays, you might use your phone quite a bit to make calls or send texts or emails, and therefore you have a whole bunch of contacts in your address book. Nowadays, of course, this is very digital, but whether on iOS or Android or the like, you might have a whole bunch of names, first name and or last, as well as numbers and emails and the like. And you might be in the habit of like scrolling through on your phone all of those names to find the person you want to call. It's probably sorted alphabetically by first name or last name, A through Z, or some other symbol. And this is frankly quite the same as we used to do, back in my day of CS50, when we just used a physical book. In this physical book might be a whole bunch of names alphabetically sorted from left to right, corresponding to a whole bunch of numbers. So suppose that in this old Harvard phone book, we want to search for John Harvard. We might, of course, start quite simply at the beginning here, looking at one page at a time. And this is an algorithm. This is like literally step by step looking for the solution to this problem. In that sense, if John Harvard's in the phone book, is this algorithm, page by page, correct, would you say? Yes. Like if John Harvard's in the phone book, obviously I'm eventually going to get to him. So that's what we mean by correct. Is it efficient? Is it well designed, would you say? No, I mean, this is going to take forever, even just to get to the J's or the H's, depending how this thing's sorted. All right, well, let me go a little faster. I'll start like 2 pages at a time. 2, 4, 6, 8, 10, 12, and so forth. Sounds faster. Is faster. Is it correct? OK, why is it not correct? Yeah. Exactly. If I start on an odd number of pages and I'm going 2 at a time, I might miss pages in between. And if I therefore conclude when I get to the back of the book there was no John Harvard, I might have just erred. This would be, again, one of these bugs. But if I try a little harder, I feel like there's a solution. We don't have to completely throw out this algorithm. I think we can probably go roughly twice as fast still. But what should we do instead to fix this? Yeah, I'm back. Nice. So I think what many of us, most of us, if we even use this technology anymore these days, we might go roughly to the middle of the phone book just to kind of get us started. And now I'm looking down. I'm looking for J, assuming first name, J Harvard. And it looks like I'm in the M section. So just to be clear, what should I do next? OK, and presumably it is. John Harvard would be to the left of this. So here's an opportunity to figuratively and literally tear this particular problem in half, throw half of the problem away. It's actually pretty easy if you just do it that way. The hard way is this way. But I've now just decreased the size of this problem really in half. So if I started with like 1,000 pages of phone numbers and names, now I'm down to 500. And already, we haven't found John Harvard, but that's a big bite out of this problem. And I do think it's correct, because if J is to the left of M, of course, he's definitely not going to be over there. And I think if I repeat this, again, dividing and conquering, if you will, here I might have gone a little too far. Now I'm in like the E section. So let me tear the problem in half again, throw another 250 pages away, and again repeat, dividing and conquering until finally, presumably, I end up with just one page of a phone book on which John Harvard's name either is or is not. But because of the algorithm you propose step by step, I know that he's not in anything I discarded. So dramatic as that might have been made out to be, it's actually just harnessing pretty good human intuition. Indeed, this is what programming's all about too. It's not about learning a completely new world, but really just how to harness intuition and ideas that you might already have and take naturally, but learning how to express them now more succinctly, more precisely, and using things called programming languages. Why is an algorithm like that, if I found John Harvard, better than ultimately just doing the first one or even the second and maybe doubling back to check those even pages? Well, let's just look at a little chart here. Again, we don't have to get into the nuances of numbers, but if we've got like a chart here, XY plot, on the x-axis here I claim is the size of the problem. So measured in the numbers of pages in the phone book. So the farther you go out here, the more pages are in the phone book. And here we have time to solve on the y-axis. So the higher you go up, the more time it's going to be taking to solve that particular problem. So let's just arbitrarily say that the first algorithm, involving like n pages, might be represented graphically like this. No matter the slope, it's a straight line, because there's presumably a one-to-one relationship between numbers of pages and number of seconds, or number of page turns. Why? If the phone company adds another page next year because some new people move to town, that's going to require one additional page for me, 1-to-1. If, though, we use the second algorithm, flawed though it was, unless we double back a little bit to fix someone being in between, that's too going to be a straight line, but it's going to be a different slope, because now there's a 2-to-1 or a 1-to-2 relationship, because I'm going 2 pages at a time. So if the phone company adds another page, that's going to take me only, or another 2 pages, that's still only just one more step. And you can see the difference if I kind of draw this. If this is the phone book in question, this number of pages, it might take this many seconds on the yellow line to represent or to solve, to find someone like John Harvard. But of course, on the first algorithm, the red line, it's literally going to take twice as many steps. And what do the n's here mean? N is the go-to variable for computer scientist or programmer, just generically representing a number. So if the number of pages in the phone book is n, the number of steps the second algorithm would have taken would be, in the worst case, n over 2. Half as many because you're going twice as fast. But the third algorithm, actually, if you recall your logarithms, looks a little something like this. There's a fundamentally different relationship between the size of the problem and the amount of time required to solve it that technically is log-based to of n, but it's really the shape that's different. And the implication there is that if, for instance, Cambridge and Allston, 2 different towns here in Massachusetts, merge next year, and there's just one phone book that's twice as big, no big deal for that third and final algorithm. Why? You just tear the problem one more time in half, taking one more byte. That's it. Not another 1,000 bytes just to get to the solution. And put another way, you could walk out way, way, way out here to a much bigger phone book, and ultimately, that green line is barely going to have budged. So this then is just a way of now formalizing and thinking about what the performance or quality of these algorithms might be. And before we now make one more formalization of the algorithm itself, any questions then on this notion of efficiency or now performance of ideas? Yeah. A lot of phone books over the years, and if you or your parents have any more still somewhere, we could definitely use them because they're hard to find. Other questions? But thanks. Other questions here too? No. Oh, was that a murmur? Yes, over here. Sorry, say again? Oh, yeah, hopefully, and then we could, then we'd have a little something more to use here. So now, if we want to formalize further what it is we just did, we can go ahead and introduce this, a form of code, aka pseudocode. Pseudocode is not a specific language. It's not like something we're about to start coding in. It's just a way of expressing yourself in English or any human language succinctly, correctly, toward an end of getting your idea for an algorithm across. So for instance, here might be how we could formalize the code, the pseudocode for that same algorithm. Step 1 was pick up the phone book, as I did. Step 2 might be open to the middle of the phone book, as you proposed that we do first. Step 3 was probably to look down at the page, as I did. And step 4 gets a little more interesting, because I had to quickly make a decision and ask myself a question. If person is on page, then I should probably just go ahead and call that person. But that probably wasn't the case, at least for John Harvard. And I opened to the M section. And so there's this other question I should now ask. Else, if the person is earlier in the book, then I should tear the problem in half as I did, but go left, so to speak. And then not just open to the middle of the left half of the book, but really just go back to step 3. Repeat myself. Why? Because I can just repeat what I just did, but with a smaller problem, having taken this big bite. But if the person was later in the book, as might have happened with a different person than John Harvard, then I should open to the middle of the right half of the book, again go back to line 3. But again, I'm not going to get stuck doing something forever like this because I keep shrinking the size of the problem. Lastly, the only possible scenario that's left, if John Harvard is not on the page and he's not to the left and he's not to the right, what should our conclusion be? He's not there, he's not listed, and so we need to quit in some other form. Now, as an aside, it's kind of deliberate that I buried that last question at the end, because this is what happens all too often in programming, whether you're new at it or professional, just not considering all possible cases, corner cases, if you will, that might not happen that often, but if you don't anticipate.
I gotta go to the bathroom and brush my teeth, guys, so I am gonna do that real quick.
anticipate them in your own code, pseudocode or otherwise, this is when and why programs might crash. Or you might see stupid little spinning beach balls or hourglasses, or your computer might reboot. Why? It's doing something sort of unpredictable if a human, maybe myself, didn't anticipate this. Like, what does this program do if John Harvard's not in the phone book if I had omitted lines 12 and 13? I don't know. Maybe it would behave differently on a Mac or PC because it's sort of undefined behavior. And these are the kinds of omissions that, frankly, you're invariably going to make. Bugs you're going to introduce, mistakes you're going to make early on, and me too 25 years later, but you'll get better at thinking about those corner cases and handling anything that can possibly go wrong, and as a result, your code will be all the better for it. Now, the problem ultimately with learning how to program, especially if you've never had experience, or even if you do, but you learned one language only, is that they all look a little cryptic at first glance. But they do share certain commonalities. And in fact, we'll use this pseudocode to define those first. Highlighted in yellow here are what henceforth we're going to start calling functions. Lots of different programming languages exist, but most of them have what we might call functions, which are actions or verbs that solve some smaller problem. That is to say, you might use a whole bunch of functions to solve a bigger problem, because each function tends to do something very specific or precise. These then, in English, might be translated in code, actual computer code, to these things called functions. Highlighted in yellow now are what we might call conditionals. Conditionals are things that you do conditionally based on the answer to some question. You can think of them kind of like forks in the road. You go left or go right or some other direction based on the answer to some question. Well, what are those questions? Highlighted now in yellow are what we would call Boolean expressions, named after a mathematician last name Boole, that simply have yes, no answers. Or if you prefer, true or false answers, or heck, if you prefer, 1 or 0 answers. We just need to distinguish one scenario from another. The last thing manifest in this pseudocode is what I might highlight now and call loops. Some kind of cycle, some kind of directive that tells us to do something again and again, so that I don't need a 1,000-line program to search a 1,000-page phone book. I can get away with a 13-line program, but sort of repeat myself inherently in order to solve some problem until I get to that last step. So this then is what we might call pseudocode. And indeed, there are other characteristics of programs that we'll touch on before long, things like arguments and return values, variables, and more. But unfortunately, in most languages, including some we will very deliberately use in this class and that everyone in the world these days still uses, is programs tend to look like this. This, for instance, is a distillation of that very first program I wrote in 1996 in CS50 itself, just to print something on the screen. And in fact, this version here just tries to print quote unquote hello world, which is, dare say, the most canonical first thing that most any programmer ever gets a computer to say just because. But look at this mess. I mean, there's a hash symbol, these angled brackets, parentheses, words like int, curly braces, quotes, parentheses, semicolons, and backslashes. I mean, there's more overhead and more syntax and clutter than there is an actual idea. Now, that's not to say that you won't be able to understand this before long, because honestly, there's not that many patterns. Indeed, programming languages have typically a much smaller vocabulary than any actual human language. But at first, it might indeed look quite cryptic. But you can perhaps infer, I have no idea what these other lines do yet, but hello world is presumably, quote unquote, what will be printed on the screen. But what we'll do today, after a short break, and set the stage for next week, is introduce these exact same ideas in just a bit using Scratch, something that you yourselves might have used when you're quite younger, but without the same vocabulary applied to those ideas. And the upside of what we'll soon do using Scratch, this graphical programming language from our friends down the road at MIT, it'll let us today start to drag and drop things that look like puzzle pieces that interlock together if it makes logical sense to do so, but without the distraction of hashes, parentheses, curly braces, angled brackets, semicolons, and things that are quite beside the point. But for now, let's go ahead and take a 10-minute break here, and when we resume, we will start programming. So this on the screen is a language called C, something that we'll dive into next week. And thankfully, this now on the screen is another language called Python that we'll also take a look at in a few weeks before long, along with other languages along the way. Today, though, and for this first week, week 0 so to speak, we use Scratch because, again, it will allow us to explore some of those programming fundamentals that will be in C and in Python and in JavaScript and other languages too, but in a way where we don't have to worry about the distractions of syntax. So the world of Scratch looks like this. It's a web-based or downloadable programming environment that has this layout here by default. On the left here, we'll soon see, is a palette of puzzle pieces, programming blocks that represent all of those ideas we just discussed. And by dragging and dropping these puzzle pieces or blocks over this big area and connecting them together, if it makes logical sense to do so, we'll start programming in this environment. The environment allows you to have multiple sprites, so to speak, multiple characters, things like a cat or anything else, and those sprites exist in this rectangular world up here that you can full screen to make bigger. And this here, by default, is Scratch, who can move up, down, left, right, and do many more things too. And within Scratch's world, you can think of it as perhaps a familiar coordinate system with x's and y's, which is helpful only when it comes time to position things on the screen. Right now, Scratch is at the default 0, 0, where x equals 0 and y equals 0. If you were to move the cat way up to the top, x would stay 0, y would be positive 180. If you move the cat all the way to the bottom, x would stay 0, but y would now be negative 180. And if you went left, x would become negative 240, but y would stay 0. Or to the right, x would be 240, and y would stay 0. So those numbers generally don't so much matter because you can just move relatively in this world, up, down, left, right. But when it comes time to precisely position some of these sprites or other imagery, it'll be helpful just to have that mental model of up, down, left, and right. Well, let's go ahead and make perhaps the simplest of programs here. I'm going to switch over to the same programming environment now for a tour of the left-hand side. So by default, selected here are the category in blue, motion, which has a whole bunch of puzzle pieces or blocks that relate to motion. And whereas Scratch, as a graphical language, categorizes things by the type of things that these pieces do, we'll see that throughout this whole palette, we'll have functions and variables and conditionals and Boolean expressions and more, each in a different color and shape. So for instance, moving 10 steps or turning one way or the other would be functions categorized here as things like motion. Under looks in purple, you might have speech bubbles that you can create by dragging and dropping these that might say hello or whatever for some number of seconds. Or you could switch costumes, change the cat to look like a dog or a bird or anything else in between. Sounds too, you can play sounds like meow or anything you might import or record yourself. And then there's these things Scratch calls events. And the most important of these is the first, when green flag clicked. Because if we look over to the right of Scratch's world here, this rectangular region has this green flag and red stop sign up above, one of which is for play, one of which is for stop. And so that's going to allow us to start and stop our actual programs when that green flag is initially clicked. But you can listen for other types of events. When the space bar is pressed or something else. When this sprite is clicked or something else. And here you already see a programmer's incarnation of things you and I take for granted every day now on our phones. Anytime you tap an icon or drag your finger or hit a button on the side, these are what a programmer would call events. Things that happen and are often triggered by us humans, and things that a program, be it in Scratch or Python or C or anything else, can listen for and respond to. Indeed, that's why when you tap the phone icon on your phone, the phone application starts up because someone wrote software that's listening for a finger press on that particular icon. And so Scratch has these same things too. Under control in orange, you can see that we can wait for 1 second or repeat something some number of times, 10 by default, but we can change anything in these white circles to anything else. There's another puzzle piece here, forever, which implies some kind of loop where we can do something again and again. And even though it seems a little tight, there's not much room to fit something there, Scratch is going to have these things grow and shrink however we want to fill similarly shaped pieces. And here's those conditionals. If something is true or false, then do this next thing. And that's how we can put in this little trapezoid-like shape some form of Boolean expression, a question with a yes, no, true, false, or 1-0 answer, and decide whether to do something or not. You can combine these things too. If something is true, do this, else do this other thing. And you can even tuck one inside of the other if you want to ask 3 or 4 or more questions. Sensing too is going to be a thing. You can ask questions, aka Boolean expressions like, Is the sprite touching the mouse pointer, the arrow on the screen, so that you can start to interact with these programs? What is the distance between a sprite and a mouse pointer? You can do simple calculations just to figure out maybe if the enemy is getting close to the cat. Under operators, some lower level stuff like math, but also the ability to pick random numbers, which for a game is great, because then you can kind of vary the difficulty or what's happening in a game without the same game playing the same way every time. And you can combine ideas. Something and something must be true in order to make that kind of decisions before. Or we can even join two words together. It says apple and banana by default, but you can type in or drag and drop whatever you want there to combine multiple words into full, larger sentences. And then lastly down here, there's in orange things called variables. In math, we've obviously got x and y and whatnot. In programming, we'll have the same ability to sort of store in these named symbols, x or y, of values that we care about, numbers or letters or words or colors or anything ultimately. But in programming, you'll see that it's much more conventional not to just use simple letters like x and y and z, but to actually give variables full words or singular or plural words to describe what they are. And then lastly, if this isn't enough colors, blocks for you, you can create your own blocks. And indeed, this is going to be a programming principle we'll apply today and with the first problem set, whereby once you start to assemble these puzzle pieces and you realize, oh, would have been nice if those several pieces could have just been replaced by one had MIT thought to give me that one puzzle piece, you yourself can make your own blocks by connecting these all together, giving them a name, and boom, a new puzzle piece will exist. So let's do the simplest, most canonical programs here, starting up with control. And I'm going to click and drag and drop this thing here when green flag clicked. And then I'm going to grab one more, for instance, under looks. And under looks, I'm going to go ahead and just say something like, initially, not just hello, but the more canonical hello, comma, world. Now, you might guess that in this programming environment, I can go over here now and click the green flag, and voila, hello, comma, world. So that's my first program, and obviously much more user-friendly than typing out the much more cryptic text that we saw on the screen that you, too, will type out next week. But for now, we'll just focus on these ideas, and in this case, a function. So what is it that just happened? This purple block here is say. That's the function. And it seems to take some form of input in the white oval, specifically hello, comma, world. Well, this actually fits the paradigm that we looked at earlier of just inputs and outputs. So if I may, if you consider what this puzzle piece is doing, it actually fits this model. The input in this case is going to be hello, comma, world in white. The algorithm is going to be implemented as a function by MIT called say. And the output of that is going to be some kind of side effect, like the cat and the speech bubble are saying hello, world. So already, even that simple drag and drop mimics exactly this relatively simple mental model. So let's take things further. Let's go ahead now and make the program a little more interactive so that it says something like hello, David, or hello, Carter, or hello to you specifically. And for this, I'm going to go under sensing. And you might have to poke around to find these things the first time around. And I've done this a few times, so I kind of know where things are and what color. There's this function here, ask what's your name, but that's in white, so we can change the question to anything we want. And it's going to wait for the human to type in their answer. And this function called ask is a little different from the say block, which just had this side effect of printing a speech bubble to the screen. The ask function is even more powerful in that after it asks the human to type something in, this function is going to hand you back what they typed in the form of what's called a return value, which is stored ultimately in, by default, this thing called answer. This little blue oval here called answer is, again, one of these variables that in math would be called just x or y. But in programming, we're saying what it does. So I'm going to go ahead and do this. Let me go ahead and drag and drop this block. And I want to ask the question before saying anything. But you'll notice that Scratch is smart, and it's going to realize I want to insert something in between. And it's just going to move things up and down. I'm going to let go and ask the default question, what's your name? And now if I want to go ahead and say hello, David or Carter, let's just do hello, comma, because I obviously don't know when I'm writing the program who's going to use it. So let me now grab another looks block up here, say something again. And now let me go back to sensing and now grab the return value represented by this other puzzle piece. And let me just drag and drop it here. And notice it's the same shape, even if it's not quite the same size. Things will grow or shrink as needed. All right, so let's now zoom out. Let me go and stop the old versions, because I don't want to say hello world anymore. Let me hit the green flag, and what's my name? All right, David, enter. Huh. All right, maybe I just wasn't paying close enough attention. Let me try it again. Green flag, D-A-V-I-D, enter. This seems like a bug. What's the bug or mistake, might you think? Yeah. Yeah, we kind of want to combine them in the same text box. And it's, it's technically a bug because this just looks kind of stupid. It's just saying David after I ask for my name. I'd like it to say maybe hello, then David, but it's just blowing past the hello and printing David. But let's put our finger on why this is happening. You're right for the solution, but what's the actual fundamental problem? In back?
This is just
Perfect. I mean, computers are really darn fast these days. It is saying hello. All of us are just too slow in this room to even see it, because it's then saying David on the screen so fast as well. So there's a couple of solutions here, and yours is spot on. But just to poke around, you'll see the first example of how many ways in programming, be it Scratch or C or Python or anything else, that there are going to be to solve problems. And we'll teach you over the course of this weeks. Sometimes some ways are better relatively than others, but rarely is there a best way necessarily, because again, reasonable people will disagree. And what we'll try to teach you over the coming weeks is how to kind of think through those nuances. And it's not going to be obvious at first glance, but the more programs you write, the more feedback you get, the more bugs that you introduce, the more you'll get your footing with exactly this kind of problem solving. So let me try this in a couple of ways. Up here would be one solution to the problem. MIT anticipated this kind of issue, especially with first-time programmers. And I could just use puzzle piece that says, say the following for 2 seconds or 1 second or whatever, then do the same with the next word. And it might be kind of a bit of a pause. Hello, 1 second, 2 seconds. David, 1 second, 2 seconds. But at least it would look a little more grammatically correct. But I can do it a little more elegantly as you proposed. Let me go ahead and throw away one of these blocks. And you can just drag and let go, and it'll delete itself. Let me go down to operators, because this join block here is the right shape. And so even if you're not sure what goes where, just focus on the shapes first. Let me drag this over here. And it grew to fill that. Let me go ahead and say hello, comma, space. And now it could just say by default hello, banana. But let me go back to sensing. Drag answer, and that's going to drag and drop there. And so now notice we're sort of stacking or nesting one block on another so that the output of one becomes the input to another. But that's OK here. Let me go ahead and zoom out, hit stop, and hit play. All right, what's your name? DAVID, enter. And voila, now it's presumably as we first intended. So thank you. Thank you. No -2 this time. So
wow.
Consider that even with these, this additional example, it still fits the same mental model, but in a little more interesting way. Here's that new function, ask something and wait. And notice that in this case, too, there's an input, otherwise known henceforth as an argument or a parameter, programming speak for just an input in the context of a function. And if we use our drawing as before to represent this thing here, we'll see that the input now is going to be, quote unquote, what's your name? The algorithm is going to be implemented by way of this new puzzle piece, the function called ask.